In the last video, we took a look at some ideal gas processes and used them to recover some of the classic ideal gas laws that people would typically learn in a chemistry course. Here we're going to spend some time looking at heat transfer processes, and I find it as a great working example to think about making what is indisputably nature's most perfect food. So I am drawing an oven here, and we have a window so we can look in, of course. So here's my rack. Let's go ahead, because it'll simplify things a bit, let's go ahead and assume it is an electric oven. So we will have a cal rod down in the bottom of the oven that is getting heated up by electric current passing through it. And then we will have here a cookie sheet. And on top of the cookie sheet is, of course, nature's most perfect food. That's right, chocolate chip cookies. Now, chocolate chip cookies are a very serious business. You very much want to have a crispy underside, but still a bit of a gooey upper side. Definitely want to go with chocolate chips rather than chunks, because if you do the chunks, by the time the chunks fully melt, then you've kind of overdone the tops, right? So that's a bit of an issue. I'll leave it to your discretion whether to put nuts in there, although I would argue for the purest approach. Anyway, to understand how we get all of this to happen, we'll go and take a look at the three ways by which heat can be transferred. So I'll start with the most efficient of the processes, and that is conduction. So this we've already looked at a bit before. This is when we have direct contact and the atoms in one object can directly collide with the atoms in another object, thereby imparting thermal energy. So I'm just going to note that like that, just draw a little arrow there. So that's conduction via direct contact. Since this is the most efficient means of heat transfer, this is why the bottoms of the cookies are going to crisp up faster than the tops. Or more efficiently transferring heat into the cookie. Now, of course, you don't want to take this too far or you'll burn it. One of the added bonuses is that you get to initiate the Maillard reaction, which is basically applying heat to the types of proteins found in flour. Will cause some of them to turn into sugars, a process called caramelization, which will make the cookie taste extra yummy. This is also, by the way, why people tend to like toasting their bread. Same kind of deal. The toaster breaks apart some of the proteins on the surface of the slice of bread to make sugars. Okay. Now, the second most efficient way of transferring heat is via convection. Even if you don't have a convection is still happening in your oven. I'll get into the difference in a moment. So this is heat transfer by means of a fluid. So here what's happening is the cal rod is heating up the air, and eventually you set up a pattern where the hot air is coming up along the edges of the oven and falls down on top. So this is primarily responsible for heating the top sides of the cookie. But since it's less efficient than conduction, by the time the bottoms are crisped up, if you've done this right and followed your recipe correctly, the tops will be still nice and gooey and the chocolate will have just melted. Now finally, you notice that a lot of recipes will tell you to, and real quickly, the difference between this convection and in a convection oven is, in the case of a convection oven, there's a fan in the oven to force the process along to make it more efficient than it would naturally be. Now for the other important issue. A lot of cookie recipes will unfortunately tell you that you should rotate your tray halfway through cooking. Now, depending on how well built your oven is, you may just plain have to do that. But the problem with it is if you open it up, all that hot air falls out, and then you got to reestablish the convection cell, and that totally ruins everything. But there's a lot you can do to prevent the need to rotate the sheet of cookies midway through the baking, and that's if you clean your oven. So what's going on here? The least efficient method of heat transfer, but still there, is radiation. So this is transference by way of light, so photons. It turns out that all objects that will give off light just because they're hot. The hotter they are, the more and more toward the blue end of the spectrum it goes. So when you look at the cal rod on your oven, you'll notice that it's sort of a dull cherry red. That's actually because as things go, it's comparatively cool. It's, say, not as hot as certain kinds of welders and stuff like that. And so the peak of the spectrum is actually in the infrared. And what you're seeing is sort of the tail end of the spectrum, which is in the reds, where our eyes can see things. But the cal rods in your oven are busy radiating off all these photons of light, mostly in the infrared. These photons will get absorbed by the oven walls and then re-emitted. And so the photons can go rattling all around, and they will eventually land on the cookie and heat up the cookie. So if you don't clean your oven regularly, all of that burnt up bits of pizza cheese and stuff like that splattered all over the oven, that one casserole that you've kind of forgot about and then bad things happened, we won't talk about that one. If you leave all that splatter on there, it turns out that part of the surface of the oven will be less efficient both at absorbing and at re-radiating the photons. So this means that that there will be sort of hot and cold spots along the oven walls, which means that the infrared radiation striking the cookies won't strike uniformly. Now, a lot of recipes will tell you, that's why a lot of recipes will tell you to spin the cookie tray halfway around during cooking. And that's to make up for the hot and cold spots. But I would say now that most ovens come with a self-cleaning cycle, just run that cycle occasionally so you have nice clean oven walls, and then you'll greatly reduce the probability of needing to spin the cookie sheet around halfway and thus maintain the convection cell in the fluid. By the way, it turns out that conduction and radiation are very straightforward to model computationally. And modeling convection is insanely difficult. But the best techniques we have are doing what's called computational fluid dynamics, where you basically just computer simulate the motion of parcels of fluid. In a rather famous/infamous case, a company that was developing computational fluid dynamics software helped to solve one of the great mysteries that had been known to beer drinkers. And that is that if you look at a pint of Guinness that has been poured, first off, everyone kind of notices that the head in Guinness is a little funny compared to other beers, and that the bubbles seem to be falling down. And there's a whole big argument, was this some sort of an optical illusion? What was going on? And eventually the resolution came about like this. So if you've got your pint of Guinness all poured and sitting on the bar. Whoops, let me more properly arc that. There we go. Remember, there's usually a slug of glass down there. But anyway, it's sitting on the bar. Let's go ahead and draw in the head. There we go. So what's happening is heat is getting transferred from the bar surface into the beer. Now, of course, it's also happening via convection from the fluid of the air, because remember, both liquids and gases can be fluids. But the most efficient transfer is, again, by direct contact from the bar via conduction. Now, what this winds up doing, though, is in order to transfer the heat within the rest of the beer, the convection cell sets up. And unlike your oven where it's coming up the outsides and falling down on the insides, what some modelers were able to show, and they wound up getting a ton of free advertising as this hit a news cycle, is that the convection cell goes up in the middle of the Guinness and falls down along the edges of the glass. Now, it turns out that the fluid, that Guinness as a fluid, is so viscous that it actually drags the carbonation bubbles with it as the convection cell happens. So it's not an optical illusion. What you're actually watching, if you see the bubbles falling down, is the entire mass of beer going down and dragging the bubbles with it. The bubbles then come up through the middle, and that's why you always tend to see this bit of a lump right in the center of the glass on the head, because all the bubbles are coming up in the middle. But it's so viscous, the head doesn't dissolve quickly, nor does it even spread out quickly. So you get that funny little lump in the middle as well as a result. So anyway, you can use that to potentially win some bets. So convection is like I say, it's bleeding edge stuff. It's way beyond the scope of this course to properly model. But we can take a look both at conduction and at radiation. So let's take a look at both of those in turn, and we'll build a working example in each case. So let's imagine here that we've got a heat reservoir that's saying at 100 degrees C. Now, this is not going to be a heat transfer diagram, just some object that we can maintain at 100 degrees C, like a kettle of boiling water, something like that. And now let's just go ahead and say that we've got that hooked up to an aluminum rod that we are going to that we then attach to a cold reservoir that we maintain at, let's say, 20 degrees C, room temperature. So this could be actually, say, maybe like a very thick stock pot or something like that. I don't know, with an immersion heater in it. So anyway, there will be a net transfer of heat from hot to cold, because that's just what heat wants to do spontaneously. I want to make this a copper rod. My bad. All right, let's say the length of this is 0.1 meters. We'll say, and then I'll also turn out that the cross-sectional area is really going to matter, so I'm just going to dimension that in and say that's 0.1 square meters. All right. It turns out the rate at which heat gets transferred goes directly as the cross-sectional area, inversely as the length, and as the change in temperature. Now, this K is not Boltzmann's constant, annoyingly. It is a number you have to look up for the particular material in question. It's called the thermal conductivity. The units for this will work out to be watts per meter Kelvin. So let's try to at least argue why this would make sense. The greater the change in temperature, difference in temperature between the hot and the cold reservoir here, means the greater the difference in the average thermal energy of each molecule. So that means collisions here will be more violent, and then as the heat transfers along here, you'll have to have collisions between the copper atoms in adjacent layers. But with a greater temperature difference being maintained, there's going to be a gradient of temperature going along here from hot to cold. And the more rapidly that gradient changes, the more violent the collisions will be between adjacent layers. So a greater rate at which thermal energy is being transferred. What's going to mess that up is the length. The longer this is, that will serve to make the temperature difference between adjacent layers of the copper rod be less, which would mean less violent collisions, which would mean a slower rate of of transferring thermal energy. Now, the thermal conductivity is specific to the details of the molecular structure, but to take a look at some extremes, the tile. Let's just go take a look at what makes a good thermal conductor. A good thermal conductor turns out to be, say, something like copper. Gold is really good. Silver is really good. You might start thinking, you tend to make money out of all those coins. Is that a coincidence? No. It turns out that the properties of the coinage metals, what makes them really good to work with, they're high malleability so that they can be struck readily, is due to the fact that the valence electron structure is just a shared electron C. So it's fairly easy to move the actual nuclei around to reshape something to look like, say, a coin or something like that. Well, it also turns out that with this shared electron C, the electrons, being incredibly lightweight and in a shared C, are also incredibly mobile. They're what transfer the heat. Because remember, it's the little, if you remember bouncing like a ping pong ball against a tank, the tank doesn't really change its momentum, but the ping pong ball sure does. Same kind of deal here. So lightweight particles that are highly mobile, it turns out that good conductors of electricity tend to be ductile metals, also tend to be good transmitters of heat. And sort of the same the other way around. In a house, you tend to use things like fiberglass for insulation, and that serves two purposes. It turns out that the glass itself that the fiberglass is made out of is both a very poor conductor of heat and electricity, for that matter. And this is because the electrons are bound to particular molecules, so they're not just free to hop around. You need to have molecule by molecule collisions, which is not as efficient as having electrons getting knocked around. So that's part of it. But another part of it is that the nature of the fiberglass also traps a lot of air. And turns out that air is actually a pretty poor conductor of heat if it's not allowed to move around. It does a decent job by convection, but if you can just trap it and keep it from moving, so you're just having to rely on nearest neighbor collisions, same kind of deal. It's not really good at it. So that's why things like fiberglass insulation and air have low thermal conductivities. If you go and buy insulation at the big box store or whatever, they actually quote what's called an R value. This is actually a thermal resistivity, which is the inverse of the thermal conductivity. So if the thermal conductivity is high, the resistivity is low, and vice versa. And since people generally go with the whole notion that big numbers are better numbers, R factors are inverse thermal conductivities, so that if it's a lousy conductor of heat, you'll have a high R factor, and you'll know to go and buy a sufficiently large amount. And so, yeah. So anyway, let's go ahead and figure out, say, the rate at which heat is being transferred with this copper. So we expect that copper should be moving heat pretty darn fast, even for a relatively small cross-section like this, just because copper, being a good conductor of electricity, is also a good conductor of heat. So sure enough, if you go look up the number in the tables, you won't have a hard and fast number when you look in tables, but it'll be around 400 watts per meter Kelvin. And the reason that the number won't be a hard and fast number is it depends on details like the exact alloy that they were using to make the table. So we said that has a cross-sectional area of a square meter over a length of 1/10 of a meter. And then this is times 100 degrees C minus 20 degrees C. Now 100 minus 20 is going to be is 80 C degrees, and a C degree is the same thing as a Kelvin. So you can write that as 80 Kelvin. So you could just left this as degrees C. But if you're not sure, it's never a mistake to just go and convert those to Kelvin, and then you know for sure that you'll be okay. But generally speaking, if you have a temperature difference, there's no need to convert Celsius to Kelvin, because when you take the difference, a C degree is a Kelvin. All right, so you go ahead and multiply all that through, and you get 32,000 joules per second. Remember, a joule per second is also a watt. So 32 kilowatts, yowza. That is indeed moving heat real quick. So you would have to be dumping an awful lot of energy in to maintain this at 100, and you got to be melting, I don't know what you're doing here, melting a bunch of ice or something to maintain this at 20. Okay. Like I said, we're not going to talk about trying to model convection computationally, because you mostly just have to model the specific situation in a computer. But it turns out that we can model the radiation pretty well. And in this context, this gets called blackbody radiation. A black body is sort of a theoretical construct that physicists use to derive the relationships. But the end result is the rate at which heat is either radiated off or absorbed. It's a two-way street. Goes as E here, which is the emissivity of the material. So this is just saying how efficient it is at radiating or absorbing heat. Again, it's a two-way street, same number both ways. It's a number that will run between 0 and 1, and it's literally just a number. There's no units. A will be the surface area of the object. And here, since this isn't a delta T, this is the absolute temperature. And so this means you will have to work in kelvins. Or, I mean, you could work in Roncanes, I suppose, if you want. But you'll have to work in kelvins here. You do have to convert to Kelvin if they give you something in Celsius. This sigma is known as the Stephon Boltzmann constant. So this funky letter here that I've been drawing, this is a lowercase Greek sigma. You draw it like that. And it is equal to 5.67 times 10 to the negative 8 watts per meter squared Kelvin to the 4. Now, as far as remembering units go, honestly, the only way I can remember the units is to remember this equation and then figure out what the units need to be. This is joules per second over here, so this is watts. I got some square meters here that I'm going to have to divide by. I've got a whole bunch of powers of kelvins I have to divide by. So that's literally how I remember it. Watts per meter squared Kelvin to 4 for the units. But The number is kind of easy to remember. You can just think about going 5, 6, 7, 8. Okay. So it turns out that although this is the least efficient channel, we've already seen it matters. Otherwise, that's why you have to have a clean oven in order to do a proper job of baking chocolate chip cookies. But it also turns out that in certain circumstances, it's literally all you've got available to you. So, for instance, looking at a satellite, let's say you have a satellite that's in deep space. And we're interested in what the net heat that could be radiated off is. It would still be the same kind of deal. It'd be the emissivity times sigma times A. But now the thing is, it's radiating heat out proportional to the fourth power of its temperature, but it's absorbing heat proportional to the fourth power of the ambient temperature. So this is the ambient temperature here, this T sub 0, or T naught as people usually say. Naught is British for 0, N-A-U-G-H-T. So this is, we can look at this for a couple of things. I'll do an example in just a second looking at a satellite. But also practically, this is why I say if you're worried about getting yourself overcooked in the summer, you might choose to wear a lighter colored t-shirt rather than a darker colored one. As it turns out, the emissivity does track pretty close with how light or dark the material is. So the lighter the material, lighter in color, the emissivity will be closer to 0. And the darker the material, the emissivity will be closer to 1. And of course, what really matters here is the emissivity in the infrared. A lot of materials you can just quote one number for, but sometimes you gotta be a little fussier. But in any event, a dark t-shirt will do a better job of both radiating and absorbing heat. But if the ambient temperature is really close to your body temperature, then that could actually be a bit of a problem. This is also why if you look at the packages on computer chips, they're always painted black, and that's to get the emissivity as close to 1 as possible, so they can maximize the cooling of the chip. They do all kinds of other things too, like you attach big honking heat sinks to them and then you put fans on them so that you can do all kinds of heat transfer via convection, and you force the convection with the fan. They're doing all the tricks they can, but it matters enough that they pay attention to that. Well, also, it turns out that what they do for most spacecraft is they coat the spacecraft in a very thin layer of gold. Gold will smash super duper thin. So, you can just, a couple of ounces of gold. You can completely cover a satellite with it. And it turns out that gold has an emissivity of darn near 1. So let's say you've got a satellite that is operating out in deep space. So we're talking like interstellar space. Interstellar space actually has a temperature. It's from the leftover radiation of the Big Bang, and it's about 3 Kelvin. So let's say that we've got some deep space satellite whose radioactive power sources have kind of fizzled out, and maybe the internal temperature of the satellite is roughly 50 Kelvin now, something like that, since we're out in deep space. How much heat could this satellite possibly get rid of? Well, if it's been coated in gold foil, the emissivity is 1. Sigma would be 5.67 times 10 to the negative 8 watts per square meter, Kelvin to the 4. Let's say this is a relatively small satellite with an area of, say, 2 square meters or something like that. But now here's the big deal. 50 Kelvin to the 4 minus 3 Kelvin to the 4. So this turns out to be 0.709 joules per second, or 0.709 watts, whichever way you want to think about it. So that's it. And these sorts of considerations matter a lot when engineering a satellite, because you have to keep in mind how much waste heat all the electronic circuitry is going to generate. And you can only dump it out so fast, or else what you're going to find is the temperature of the satellite goes up and you start frying your satellite, and that would be very sad. All right, in the next video, I will go ahead and revisit the second law of thermodynamics. Catch you over there.